A 59-story skyscraper in Midtown Manhattan was sitting on the edge of catastrophic collapse while people worked inside it. And the only person on Earth who knew was the engineer who designed it. William LeMessurier discovered in June of 1978 that his most famous building, Citicorp Center, could fail in 70-mile-per-hour quartering winds, the kind of storm that hit New York statistically once every 16 years, and the building had been open for exactly 1 year. Progressive collapse, engineers call it, when one joint fails and the load transfers to the next connection, and that one fails and the next, until the entire structure unzips and comes down. The math was clear, the danger was real, and LeMessurier faced a choice that would define the rest of his career because staying silent might have saved his reputation, but disclosure would almost certainly destroy it. This is the story of how a student's question revealed a fatal flaw in one of New York's most recognizable buildings, and what happened during the 4 months engineers raced to fix it while a hurricane tracked toward the coast. Welcome back to the machines we built. Today we're going inside one of the most extraordinary cover-ups and one of the most extraordinary acts of professional courage in the history of American engineering. This is Citicorp Center, and almost nobody knew what happened here for 17 years. To understand how this tower nearly became a disaster, we have to go back to the beginning, because Citicorp Center was shaped by a conflict that forced its design into something radically unconventional. The year was 1973, and Citicorp, one of the most powerful banking institutions in the world, wanted a new headquarters in Midtown Manhattan with the location already chosen at Lexington Avenue and 53rd Street, and the ambition enormous enough that what they wanted was something announcing to the entire world that this company had arrived. Standing on the northeast corner of their block, refusing to move, was a church. St. Peter's Lutheran Church had held that corner for decades, and when Citicorp came knocking, the congregation did what any institution with deep roots and deeper convictions tends to do, refusing every part of the offer, the land, the air above it, any claim on the property. Citicorp countered with something most developers would never have offered, proposing to demolish the old church entirely and construct a brand new street. Peter's at the same location at Citicorp's expense in exchange for the air rights overhead, and St. Peter's agreed. That's when the engineering problem dropped into William LeMessurier's hands. Standard high-rise construction anchors its load-bearing columns at the corners of a building's footprint because that's where weight transfers cleanest to the ground, an approach that had defined the field for generations. One corner now belonged to a church LeMessurier couldn't touch, and that constraint pushed him towards something almost nobody had attempted at this scale. 4 support columns planted at the center of each side instead, each one roughly 35 feet wide. Each one climbing 9 stories before the building began above them, lifting the entire structure 112 feet off the ground and carving out an open plaza beneath it. The engineering challenge wasn't just supporting the building's weight, but forcing that weight to travel to columns that weren't where columns were supposed to be. LeMessurier's solution involved 6 tiers of diagonal bracing running up each face of the tower, massive chevrons visible from the street. Gravity loads coming down through the building's vertical columns needed a path to reach those mid-face stilts, and at certain strategic points, LeMessurier removed sections of the vertical columns entirely, forcing the weight to divert through the diagonal braces instead. The load had nowhere else to go, and every 8 stories, half of the building's total weight, got channeled through those chevron braces, carried laterally to the center of each face, then down through the stilts to the foundation below. The braces themselves were enormous, nearly 130 feet long end to end, too large to transport intact through the streets of Manhattan, arriving in sections and getting welded together on site, piece by piece, joint by joint, until the entire chevron system stood complete. The design worked elegantly on paper, and the structure weighed approximately 22 pounds per square foot, unusually light for a building of this height, which created a different problem because the tower could sway noticeably in high winds, not enough to threaten structural integrity, but enough to make occupants uncomfortable. LeMessurier's answer to that problem had never been attempted in an American skyscraper before, installing a tuned mass damper on the 63rd floor, a 400-ton block of concrete roughly 29 feet square and 8 feet thick, resting on a thin cushion of pressurized oil. As the building swayed in one direction, the block moved in the opposite direction, its motion controlled by hydraulic shock absorbers that dissipated energy through friction, and the system reduced the building's sway by approximately 50% and saved roughly $4 million in structural steel that would have otherwise been required to stiffen the frame. Engineers in the industry called it the Great Block of Cheese, and it worked exactly as designed. St. Peter's kept its corner. Architect Hugh Stubbins capped the tower with a sloped notched roofline originally drawn up for solar panels, though that plan never advanced. And when it opened in 1977, Citicorp Center had earned a place among the most recognizable silhouettes on the Manhattan skyline, with LeMessurier's reputation already strong, rising further still. Everything from the outside appeared perfect, and for months no one had any reason to think otherwise. Then in June of 1978, a single phone call began to change everything. A Princeton University student named Diane Hartley was working on a class project or thesis about Citicorp Center, a building already circulating through academic discussions as a case study in forward-thinking design. And Hartley was thorough enough to go further than most students would, calling LeMessurier's office directly. The question she brought carried technical weight, and it turned out to be exactly the right kind of technical. Asking what those 4 columns placed at the midpoints of each side, rather than the corners, meant for the building's ability to handle quartering winds, meaning wind striking at a 45-degree angle, catching a corner instead of a flat face. An associate at the firm fielded the call, gave Hartley a reassuring answer, and the conversation closed. But what nobody could have anticipated was what happened next, because LeMessurier heard about the inquiry and something in it refused to leave him alone. Sitting down with a pencil, he started running the math himself. LeMessurier's original design accounted for quartering winds, the chevron bracing system, the diagonal steel members running through the building's core, engineered to transfer wind loads safely to those central columns under exactly those conditions. And he carried the calculations to prove it. The building checked out and he knew it, and he kept working anyway. That's when he found what had changed during construction. The original design specified welded joints connecting the bracing members to the rest of the structure, but in the field, bolted joints had been substituted instead. Bolted connections are standard in construction and perfectly adequate across a wide range of applications, but they don't behave the same way welded connections do under stress. A welded joint fuses 2 pieces of steel together by distributing force across the entire connection and essentially making them act as a single continuous piece of metal. But a bolted joint creates discrete points of contact, and at each bolt hole, stress concentrates in specific locations rather than spreading evenly. Under the right loading conditions, those concentration points can become the first place a connection fails, running the numbers against the bolted connections that had actually been built rather than the welded ones he had drawn. LeMessurier arrived at an answer that had nothing reassuring in it, because when the math was finished, the building was far weaker than anyone had believed. Stress on certain connections had climbed to roughly 160% of what his original calculations assumed. Not a rounding error, not something a safety margin could absorb, but a number large enough to mean the joints would give way under quartering winds of around 70 miles per hour. 70 miles per hour sounds like a rare threshold, the kind of wind only a major hurricane delivers, but LeMessurier knew the wind data for New York City, and what that data showed him landed like a punch. Because once every 16 years, statistically, a storm producing those conditions would pass over Manhattan, and the building had been open for 1 year. What made the math worse was what failure would actually look like, what engineers call progressive collapse, a name that describes the mechanism accurately because one joint gives way. The load transfers to adjacent connections. Those fail under the added stress, then the next set fails, and the next. The structure unzipping from one end until it comes apart entirely, not a gradual lean or a visible crack, but a collapse. Hartley's question pointed nowhere near this flaw, because she had no way to know about the bolted joints or what they meant for the stress calculations. And the vulnerability her inquiry inadvertently touched on didn't even match what she had asked about. What her inquiry did was send LeMessurier back to his own work, and his own work led him here to a calculation describing a building in the middle of one of the most crowded places on Earth, quietly waiting for the wrong storm to arrive. At that point, the question was no longer about engineering. What LeMessurier faced in the days after that calculation is worth sitting with because the easier path couldn't have been clearer, and the temptation to take it was real. Silence carried genuine appeal. Maybe the right storm never arrived at exactly the right angle, Maybe the building stood for decades without incident. Maybe nobody ever found out. But disclosure meant something different entirely, admitting that a structure carrying his professional signature put people in danger, opening himself to lawsuits capable of destroying his firm. Watching a career built on precision and trust become permanently attached to one of the worst engineering failures in American history. Plenty of people facing that choice choose silence. LeMessurier went to his attorney first, then to Citicorp, then to architect Hugh Stubbins, laying out everything in sequence: the flaw, the calculations, the risk, the 16-year statistical window, to each person who needed to know it. And this is where it gets interesting, because in a 1995 New Yorker interview, he described the moment of discovery in terms that surprised the journalist recording it. Alongside the terror of what he had found, LeMessurier identified something he called a kind of gift, a problem that was uniquely his to uncover and uniquely his to solve, a framing that only makes full sense once you understand what he did next. He told the truth, and then he started fixing it. The plan that emerged from those conversations ran simple in principle and brutal in execution. Reinforce every compromised connection in the building, do it correctly, do it without triggering a panic that could cause as much harm as the flaw itself. 2-inch thick steel plates would be welded over each of the bolted connections throughout the bracing system. Every joint without exception. Not a selection, not the worst ones first and the others later, but all of them until the building could withstand exactly what it had always been designed to withstand. None of it could happen during business hours. Starting in the summer of 1978, welders moved through Citicorp Center after dark, working inside the spaces behind walls and above ceilings, through the structural cavities running the length of the building, floor by floor and joint by joint. Tenants heard construction noise and received no explanation for why the work happened, only at night, because no truthful explanation could have been given, without revealing what the work was actually for. And city officials who had been quietly briefed agreed to hold the secret while emergency evacuation plans covering several blocks around the building were drafted and kept ready. Running from June through October of 1978, 4 months of nighttime welding in the middle of New York City, carried out by workers whose names never made it into any account of what happened here, keeping one of the most consequential secrets in American architectural history, while the city slept a few floors below them. September 1978, the repairs still underway, the building not yet fully reinforced, and out over the Atlantic hurricane Ella had formed and begun tracking toward the northeastern United States. Toward New York City, everyone who knew about the flaw watched that storm track with a kind of dread that had no outlet. Because the welders were already moving as fast as they could, the joints were being reinforced one at a time, and nature doesn't wait for engineers to finish their work. The threat stood real, the timeline fixed, and nothing remained to do but keep going. Ella veered away before reaching the coast. The city came through untouched, the building came through intact, and the repairs continued. And by October 1978, the last plate sat in place, the last joint reinforced, and the building that spent over a year silently broken finally matched the structure it always appeared to be from the street below. Nobody outside that small circle of officials and engineers knew any of it took place, and none of them were talking. Life inside Citicorp Center continued without interruption, while LeMessurier held no press conference. Citicorp released nothing publicly. The city officials who had been briefed moved on to other things, and the welders who had worked through those nights gave no interviews. 17 years went by without a word of it reaching the public. Joe Morgenstern, a journalist writing for The New Yorker in the mid-1990s, picked up a thread, a rumor that something structural had happened with Citicorp Center back in the late 70s, something serious that had never reached the public. And that thread led him to LeMessurier, who had carried this story for nearly 2 decades. And that's when LeMessurier decided it deserved to be told. On May 29, 1995, The New Yorker published Morgenstern's article, The 59-Story Crisis, with LeMessurier cooperating fully, giving extensive interviews and walking through every calculation, every decision, every night of welding, every anxious check of the weather forecast during the weeks Hurricane Ella tracked toward the coast. The article landed in the engineering world like a detonation. Engineers who read it couldn't believe the silence had held so long. The public couldn't believe a skyscraper in the middle of Manhattan had been on the edge of collapse without anyone knowing. And ethicists and academics recognized it immediately as one of the most striking examples of professional self-disclosure in the history of any licensed field, opening a conversation that has never fully closed. No lawsuit came, No professional body moved to strip his license, no criminal charges were ever filed, and his firm kept operating. Citicorp's insurers covered approximately $4.3 million in repair costs and related expenses. And in the years following the 1995 revelation, LeMessurier's standing in the profession climbed, rather than collapsed. And the reason the engineering and legal communities responded that way is worth understanding, because the gut reaction to this story might not immediately account for it. LeMessurier hadn't caused a catastrophe, he had prevented one. And the way he prevented it, by walking into a room full of powerful litigious people and stating clearly that he had made a mistake, and here was exactly what it was, represented something those communities almost never see. The standard response when a professional discovers something has gone dangerously wrong is not what LeMessurier did, and across engineering, medicine, law, any field where a license carries public trust, the default move when something breaks is to say nothing, consult lawyers, hope the problem resolves itself before anyone finds out. But LeMessurier skipped all of that. The professional community chose to honor that decision rather than punish him for the underlying error. And in June 2007, at 81 years old, he died with his reputation not merely intact, but in many ways defined by the most frightening months of his career. The way this story travels sometimes compresses Hartley's role into something cleaner and more dramatic than what actually happened. And the accurate version turns out to be more interesting than the simplified one. She didn't find the flaw because finding it required access to construction documents she had never seen, and her question had nothing to do with bolted connections. Hartley was a Princeton student working on a class project or thesis thorough enough to call the engineer's office directly, and her concerns centered on whether the unusual column placement created vulnerability to quartering winds, which is exactly the kind of careful, specific question a diligent student would raise. An associate gave her a reassuring answer, and the inquiry appeared to close. But what it had actually done was lodge something in LeMessurier's mind that refused to resolve, a thread he pulled on himself, which led him back to his own calculations, which led him to the joint substitution, which led him to a number that changed everything. The flaw she inadvertently pointed toward wasn't even the thing she had asked about because it sat deeper, and it only surfaced when LeMessurier ran the math on the building that had actually been constructed rather than the one he had drawn on paper. And none of that diminishes what her question set in motion. The history of catastrophic engineering failures is packed with moments where someone raised a concern, got dismissed, and the thread went cold, where institutional pressure to stay on schedule crushed the question before it could become action. But here, that didn't happen. A student asked, an engineer listened, and a disaster that could have ranked among the worst in New York City's history never arrived. Engineering programs across the United States and internationally now teach the story of Citicorp Center, not as a lesson in structural analysis and not as a technical breakdown of which joint type performs under which loads, but as a case study in what professional responsibility actually requires when something goes wrong. Alongside the Challenger Space Shuttle disaster and the Tacoma Narrows Bridge collapse, this episode now occupies one of the central reference points in how engineers understand their obligations, not just to the design, not just to the client, but to every person who lives and works and moves through the structures they build. The National Society of Professional Engineers includes it in their ethics curriculum, and universities use it to open a harder conversation than a technical one. What a licensed professional owes the world when they discover that something they built is dangerous, and what answering that question honestly actually costs. What it cost LeMessurier amounted to months of fear and the near certainty that his career was finished. And that cost turned out to protect a building, protect a neighborhood, and 17 years later, when the story finally reached the public, protect his legacy as well. 601 Lexington Avenue, renamed from Citicorp Center in 2009, still stands at Lexington and 53rd Street in Midtown Manhattan, fully occupied and structurally sound, its sloped roofline cutting one of the most recognizable shapes against the skyline, even without the solar panels that originally justified its unusual angle. Inside the 400-ton tuned mass damper, one of the earliest high-profile applications of that technology in an American skyscraper still shifts on its cushion of oil to counteract the building's sway in high winds. And below the tower's northeast corner, St. Peter's Lutheran Church still holds its spot, still active, still known for its jazz vespers services, the congregation that refused to sell still present decades after the deal that made the whole project possible. The bolted joints that were never supposed to be there are long gone.